Alright, hey everybody. This is the second part of 10.1 significance test. So this is the second video. If you haven't gone and watched the first part, go ahead. And what we did in that first one is we worked a problem all the way through using the whole formulas, which was a little crazy. And then I showed you the calculator steps. And from here on out, you don't have to use the formulas. You can go straight through by calculator. As long as you label what you do, you're good to go. So that's what we're going to do today, is we're going to work through a couple of these examples. So for this next one, I'm looking at example 2. It says we've got, for the response bias project, Sarah and Miranda investigated whether the characteristics of the interviewer can affect the response to a survey question. So at the Tucson Mall, they asked 60 shoppers the question, do you like tattoos? For 30 of the shoppers, the interviews were wearing clothing that covered their tattoos. For the remaining 30 shoppers, the interviews showed their tattoos. The choice of showing or not showing their tattoos were determined by a coin flip. Sarah and Miranda suspected that more people would answer yes when their tattoos were showing. The results of their experiment are summarized in the two-way table below. Does this data provide convincing evidence that the interviewer showing her tattoos increases the proportion of shoppers who would say they would like a tattoo with 5% significance level? Alright, so we got all kinds of stuff to dive into with this one. Alright, so first thing, they actually give us a two-way table, so we have to write less of our organizing to start with. So first thing you want to do is label your stuff. So I'm going to make showing tattoos be P1 and not showing tattoos be P2. Alright, and we know our number of successes. That's our yes column, or the entry in the yes row, actually, for both of those. And then we know our total, our ends, because they're both 30. So the only thing we don't know, excuse me, is our P hat 1 and P hat 2. So that's what we've got to go through and calculate real quick. So P hat 1 is going to be 18 over 30, which when you mash your buttons, you get 0.6. And then P hat 2 should be 14 over 30. And that's going to give us 0.467. So those are our two P hats that we need. Alright, jumping in here for our parameter, it's going to be P1 minus P2, like it's been. And that's the difference in, I'm going to not have enough room to write this, so I'm just going to tell you. So it's the true difference in proportion of people who approve of tattoos based on if the questioner showed their tattoos. So you can reword that, you can shorten it. You need to say true difference in proportion, what you're looking for, so the proportion of what, and then what you're basing that on. Alright, for our statistic, we've got P hat 1 minus P hat 2. So P hat 1 is 0.6. P hat 2 is is 0.467. And when we subtract those out, we get 0.133. For our hypotheses, it's always for our null P1 minus P2 equals 0. That's always it. And then what we're looking for is that showing tattoos will give a higher proportion than not showing tattoos. So showing tattoos is my P1. If that's going to be bigger, when I'm subtracting, should I get a positive number or a negative number? If P1's bigger, I should have a positive number, so it should be greater than 0. And then they do tell us the significance level, so it's 5%, so 0.05, that's our alpha. Alright, so two sample z-tests for P1 minus P2. Alright, we have to do our usual conditions, so random, 10%, and large counts. For random, it is random. What they did, they don't actually say the words in there, but they say that they flipped a coin to show whether they were showing their tattoos or not. So it was random assignment. for 10%, we would assume, and it's for both of them, that 30 is less than 10% of the mall shoppers. Which means there's at least 300 people trooping through that mall that day, which seems reasonable. Unless everybody's home practicing social distancing. So then maybe not. Alright, and then the last one, it's going to take a little work, is our large counts. At this point, I've pretty much given up on writing the formula. It's just too much. So it's 30 times 0.6, 30 times 0.4, and so that's for our P1. For P2, it would be 30 times 0.467 and 30 times 0.533. That is not what I wanted to do. Stylus decided to be dumb today. Alright, 533. Seriously? There we go. Alright, so that gives us 18. This one gives us 12. This gives us 14.01. And this one gives us 15.99. Either way, they're all bigger than 10, so we're good to go. Alright, we've talked about our mean. Our mean has to be 0 for this. And then our pooled proportion. This is the p hat c that we've talked about. And so the formula for this one is on top, you add your successes from both proportions. And then on the bottom, you add your ends for both proportions. So my number of successes from P1 was 18. My number of successes from P2 was 14. And then on the bottom, they both had 30 as their sample size. So we end up with 32 over 60, which works out to be 0.53. Just a quick reminder, especially if you're using the software. So I'm here, if I hit enter, it's just going to reduce the fraction, which doesn't help because we need a decimal. So if you hit menu, 2, and then number 1 is convert to decimal. It'll convert your answer to a decimal for you. And you can, if you remember, you can also do it straight from typing the fraction in. And then you don't have to skip that middle step. Okay, so there's our general formula. You actually don't need to write that if you're doing the 2 prop Z test. So I just accidentally wrote that. Alright, so what you need to say is you just need to say that you're going to do a 2 prop Z test. And then say what you get out of it, your test statistic and your p-value. If you make that chart up at the top, you don't have to write anything else because you've labeled out your number of successes, you've labeled your total number for each of your proportions, so you're good. Alright, so to get to our 2 prop Z test, let's menu. We're going to go to statistics, which is 6. We're going to go to stat test, which is 7. And then 2 prop Z test is 6. And then we just have to go through and list everything. So 18 was our first success, and then that sample size was 30. For our P2, 14 was our number of successes. We were at 30. And now we got to go back and look at our alternate hypothesis. So my alternate hypothesis is right here. It was P1 is greater than P2. So hit that drop down and look for greater than. Alright, hit OK. And it spits it all out at you. So what we care about is the z-score, which is the very first one there, and then the p-value, the second one. So our test statistic is our z. Let me get rid of that highlighter. Alright, so z equals 1.035, and our p-value is 0.1503. Okay, so last thing we need to do is draw our picture, and then we can decide. Alright, so 0 is our mean. Our z was 1.035, and from our alternate hypothesis it was greater than, so we're shading to the right, which would be greater than. Don't forget your label, 0, 1. Okay, so looking at our p-value, we have a p-value of 0.15. That is very much not passing our alpha. It is not smaller than 0.05. Okay, so the last thing left for us to do is just do the conclusion on this problem. So since that 0.15 is not larger than, or is larger than 0.05, we fail to reject. And that means we do not have convincing evidence. Alright, the last part of that sentence is literally word for word what they asked in the question. So if you're ever struggling with trying to figure out how to write your conclusions, go back up and look. A lot of times you can just steal their wording and not have to worry about it. Alright, so that's where we are on that one. Pretty straightforward. By using 2-prop-z, it takes all of the tedious calculations out of the way and makes your life a lot easier. So I would definitely recommend going that route. Alright, let's try one more. Are teenagers going deaf? In a study of 3,000 randomly selected teenagers in 1994, 15% showed some hearing loss. In a similar study of 1,800 teenagers in 2006, 19.5% showed some hearing loss. Between the two studies, Apple introduced the iPod. If the results of the test are statistically significant, can we blame iPods for the increased hearing loss in teenagers? And then B, do these data give convincing evidence that the proportion of all teens with hearing loss has increased? Okay, so let's back up to letter A for a second. So if the results of the test are statistically significant, can we blame iPods for the increased hearing loss? Anywhere in there were we asking whether these teenagers had an iPod? Nope. So all we can say based on this test, if it is true, if it is statistically significant, if we can reject the null, all we can say is that there has been a decrease. We can't assign blame. We can't say why. We can't say causation. All we can say is that we've seen a change. So can we blame iPods? No. Oop, I can spell, I promise. Let's fix that one. Alright. Really? Okay. So let's work through this last one, going all the way through the steps. This one doesn't give us a chart, so we need to actually create our own, which is good practice. All right, so first thing you want to do is identify what you're talking about. So I'm going to use for P1, I'm going to say it's the 1994 data. And then P2 is going to be my 2006 data. All right, so my number of successes my p hat 1, and then my sample size 1. We need that. And then we'll need the same thing for P2. We need our number of successes, our P hat 2, and then our N2. Alright, so let's start with the easiest, the sample sizes. So in 94, they asked 3,000 kids, and in 2006, they asked 1,800. Alright, they went ahead and gave us the percent, so all we have to do is turn them into decimals. So 94 was a 15% hearing loss, and in 2006, it was 19.5. So turning that into a decimal, we get 0.195. Alright, now to find successes, we just need to multiply those together. So if it's 3,000 kids, let me scroll down for you. Alright, so we're at 3,000 students, and 15% of them have hearing loss. 15% of 3,000 is 450. And then we need to just go do the same thing for 2006. So we had 1,800 students, or teenagers, we don't know they're students. And there's 19.5, so 0.195. And we get 351 successes. Alright, taking the, 2 minutes to write all of that out makes everything else go so much faster. Alright, so first up is state. Alright, we need to say what our parameter is. So we're at P1 minus P2, and that's the true difference in proportion of hearing loss. From 1994 to 2006. Alright, so for the statistic, that would be p hat 1 minus p hat 2. We just found out that p hat 1 was 0.15, p hat 2 was 0.195. So when we subtract that out, we're going to get negative 0.045. Negatives are okay. Don't let that freak you out. Alright, then we got to do our hypotheses. Alright, so first is our null hypothesis, and it's always the same when we're doing these differences. P1 minus P2 equals 0. For our alternate hypothesis, we have to think about it a little bit. So what the question's asking, I'm looking at letter B, says, do these data give convincing evidence that the proportion of all teens with hearing loss has increased? If it would increase over that time, that means P2 would have to be larger. So if we did P1 minus P2, and P2 was bigger than P1, that means we would have a negative number. So that would be less than 0. Alright, and the last thing we have to do is our significance level. They don't specify, so we're going to assume our alpha is 0.05. Alright, so next up is plan. Alright, it's a 2-sample z-test for P. Alright, our random 10% and large counts. Alright, for random, they say they're randomly selected. For 10%, we're talking about randomly selected teenagers. It doesn't say the U.S., so it could be the world. We don't know. It could be a state, for all we know. But either way, 3,000 is still going to be smaller than 10%. And if 3,000 is smaller than 10%, 1,800 is definitely smaller than 10%. All right, last step for large counts. All right, so for our P1, it's 3,000 times 0.15, and then 3,000 times 0.85. Remember, that's coming from 1 minus your p hat. And then for P2, it's 1,800 times 0.195, and then 1,800 times 0.805. All right, so multiplying that out, that's 450, 2,550, 351, and 1,449. All of those are bigger than 10. So since all of those are true, we're good. We've met all our conditions, so we can go ahead and move on to the next part. All right, so we've done our state and our plan, so now we need to jump to our do. All right, so for this one, well, hang on, there we go. All right, so our mean is P1 minus P2. That's going to give us 0. We need to find our pooled proportion, so that's P hat C, and that's the number of successes for each one on top over the number of sample sizes, both sample sizes added together. So there were 450 successes from the first one. There were 351 successes from the second, and that's going to be over 3,000 plus 1,800. All right, so when we add those together, we're going to end up with 801 over 4,800. Don't forget to tell this that you want it in decimal form. And we end up with 0.167 for our pooled. All right, then we want to tell the graders that we're doing a 2 prop z test. And we need to make sure that we show out of that our z, which is our test statistic, and then our p-value. All right, so we're going to do menu, stats, which is 6, stats test, which is 7, and then 2 prop z is 6. And then we're just going to fill in our information. You can pull it straight off that chart we made up at the top. So it's 450, and the sample size was 3,000. And then for our second proportion, we had 351 for our successes and 1,800 for our sample size. And then going to our alternate hypothesis, we had less than 0. So we want the less than. Hit OK, and it's going to spit out everything we need there. So we end up with a z of negative 4.05, so I round that off, and then a p-value of 0.000026, which is super teeny tiny. Alright, so here's our picture. Here's our 0. We have negative 4.05, so that's over here. Our alternate hypothesis was less than, so we're shading to the left. Make sure you label it. And we got a p-value that is way smaller than our alpha. So we can reject this null hypothesis. Alright, I'm going to shorten that just a little bit. You know what goes there. We reject the null hypothesis because our p-value is smaller than our alpha. And we do have convincing evidence. Okay, so that's all of the examples for this week. This is all the notes that you have to take. So over the next couple days, process this as you can. Work on the homework. I'm going to try and get the homework answers up tonight. At the latest, it'll be tomorrow morning. And I will throw some extra practice problems up there for you if you'd like. I'll also give you a one sheet, and we'll go from there. So remember, there's office hours Tuesday afternoon at 4. There are office hours Friday afternoon at 1. If you need some serious one-on-one help, just send me an email. We'll schedule a Zoom meeting one-on-one, or if there's a couple of you, we can do, smaller ones. That's fine. Whatever you guys need to get through all this material. All right. We'll talk to you later. Have a good afternoon. Bye.